All right, so I'm going to talk about weather today, and of course that draws us all together, right? We agree on the weather. This is something that's obviously powerful. It impacts all of our lives, and certainly things are changing here in Ohio, and we're going to get into that a little bit. Like Glenn alluded to, I've always been fascinated with weather. I grew up in Miamisburg, Ohio. How many know where Miamisburg? Right, so several. So it's a little bit south of Dayton. And then when I was 3 years old, we moved to Miami, Florida. And even at 3, living in Florida, you're quickly intimately aware of tropical cyclones, hurricanes, and the interaction between the atmosphere and the ocean. I just really fell in love with that. A couple years later, we moved back to Miamisburg, and then in 1988, we had the big dry, of course, according to Time magazine, right? We had our big drought in 1988. That's when I officially retired from farming. This is a photo of me here, 9 years old, on the neighbor's tractor. He had all of 5 acres, so really heavily, intense ag there, right? But no, anyway, this is, I was fascinated by agriculture, but it just didn't quite overcome, the draw to weather, and that's what I was really drawn to. And so today, just to start out, and usually what I like to do is to get people to think about these big events that occur, right? We have these events that every generation can recall, and what we would call extreme events today, right? So we can go back to the flood of 1913. This is considered Ohio's greatest weather disaster still. I mean, generally 6 to 11 inches of rainfall fell across the entire state, or most of the state. And certainly this is a picture of my hometown here in Miamisburg before, obviously, the levees were put in place along the Great Miami River here, under several feet of water. And this is a photo from Columbus. And the Historical Society and Ohio History Connection have a lot of these photos from different places. And I encourage you to kind of look at that. To put our greatest weather disaster in perspective, we had Hurricane Harvey last fall. In an area of about the size of Ohio, over 20 inches of rainfall fell in about 4 to 5 days. And some locations picked up over 60 inches of rain in 4 days. Right? That's an amazing number, amazing amount of precipitation falling from the sky. And we're going to talk about the changes that we're seeing in our atmosphere that allow those types of events to happen. Hopefully not over Ohio, right? But certainly these types of events can happen. Now, one of the events that I missed was the blizzard of 78. And I wish I could have seen this. A lot of people advise against that. I was in Marion, right? Yeah, I was in Marion County last fall, and I didn't know that one of the guys on the roof here was in the audience. Is he here today? I don't think so. Right? Obviously, a lot of wind with that storm, rapidly falling temperatures, a lot of snow, blowing snow. We've had some big snowstorms, in Ohio, certainly even in Columbus, but nothing really rivals the feel, right? And this is a moment to take, to think about how we romanticize weather, right? How it becomes part of our culture. These weather events become really ingrained in our lives, and they become kind of the milestones in our lives for every generation. So now we can jump forward to a more recent time. This is a satellite image showing this huge complex of thunderstorms that blew up and moved through most of Ohio. Here, when I was actually in Dayton at the time, we were sitting about 99 degrees before this thing came through. It's a term that was used, that got picked up in the media and was used quite a bit, and that term was derecho, right? Now that's a term that we've always used, but it just became popular at the time. Long-lived line of thunderstorms that moved through, and it caused a lot of extensive damage, a lot of electricity. How many people were out without electricity for more than a week? Some of us, right? I mean, it was really intensive. So what was the big term this winter? Didn't happen here. Bomb cyclogenesis, you're right. The bomb cyclogenesis, and the poor East Coast now, 2 nor'easters in a week is pretty phenomenal as well. But, these terms, the weather is just something that we really relate to. It draws us all together, and so sometimes we become really impassioned about it. But let's step back for a second and think about what is weather, right? This is pretty simple. What is weather? Current state of the atmosphere. What's the atmosphere? Right? This thin gaseous layer of air surrounding Earth protects us from UV sunlight, right? Caused the effects of weather, or the effects of imbalances of heat, pressure, moisture moving across the surface of the Earth. Those effects are weather. And they happen rapidly. Short-term, minutes to days, I would argue seconds even, of changes, right? And so all of these are happening very rapidly. Play a video here for you. This is a series of satellite images that are stitched together for an arbitrary month from April. So we can see a series of patterns that develop, right? When we start to pull out from what's happening, we see these patterns of clouds develop. We've got these what would be rapidly moving cloud systems moving across the southern hemisphere, some across the northern hemisphere as well, but they take more of a north-south component because we have a lot more land in the northern hemisphere. Maybe you would see pulses of clouds along the equator, but this is really just to get a sense that when you step back from all these really high-frequency changes in the weather, you can start to see the patterns that develop. So how is that different in climate? A lot of times we use weather and climate interchangeably, right? The problem is they are different. The climate's really describing that long-term change, right? When we talk about normal right now, we're talking about a 30-year average temperature for March 6th from 1981 to 2010. And it does change every decade, our normal, right? It updates every decade. But these averages of the climate system over periods of a month or more are what we're talking about. Those of you who haven't seen me give this presentation yet, can you tell me what's in the picture here? It's kind of hard, right? I'll go ahead and set this one into motion too. Hopefully it'll keep going. So you see a dog and a dog walker moving along. So the dog is moving back and forth, right? So maybe there's a fire hydrant up here, right? Maybe there's a McDonald's wrapper down here. But all along the dog's moving back and forth, right? But in relationship to the dog walker. The dog walker's moving this way. We expect the dog walker to continue moving this way based on the evidence we see. And the relationship between the dog and the dog walker is very much the relationship between weather and climate. Okay? The dog being the weather, that highly variable, changeable weather, right? And climate describing that path or throughout time here. Okay? So this is keeping this metaphor in mind as we move forward in the relationships between the two. Now, weather is really tied to our perception, right? Is it cold today? Is it warm today? Is it warmer than it should be today? Those types of questions often come to mind. So we had that first week of January this year, right? We were sitting some 30, maybe 32 degrees below average at the end of the first week of January. This is a snapshot of the average temperature compared to a long-term mean, 79 to 2000, where you see the blue colors and even purple here in the Miami Valley. Again, those were temperatures some 20 to 30 degrees below average for that first week, right? Well, on this one, for instance, it was for a particular day, Wednesday. But you can see if you look across the Earth here, a lot of Alaska was warm, across Eurasia was warm. Most of this map is warm indeed for that day. Now we can flip to the end of the month. We warmed up quite a bit, right? This is one day, Friday, January 26th here. A large warm anomaly across the Midwest. Areas that were warm are now cool. So we see these changes that happen really frequently, day-to-day changes. And it's hard, it's really driven. This really helps drive our perception of what's happening. On a longer term, we can look at the annual change in temperature here. This is what I call the U.S. dog and dog walker map. This is for the contiguous U.S., right? The purple line being the dog. These are annual average temperatures from the late 1800s to the present, right? And you can see these variabilities, these warm periods during the early 1900s, cooling from the 40s to 70s, and the big warm that we've seen since then, right? The dog walker is this blue line. That's the trend. That's the trend upward. So we can look at this. This is the annual weather and the climate and see that temperatures are indeed changing here in the U.S. It's very similar to, this is from NASS, this is the grain yield, right, for corn. And we can look, if we just looked at 2 years where they're low, say 2011, 2012, that wouldn't really describe that long-term change, right? What describes that long-term change is really that blue line here where we've seen the corn yield go up and up essentially since, on this map at least, since the 1980s. Now we know what's happening at the surface of the Earth because we've been measuring it. We've been measuring it well for quite a long time, and we have other means of measuring temperatures back in time. Right? So if you think about some of the modern day observation platforms, weather stations, weather balloons, sea surface temperatures from buoys, ships, airplanes, and then since the late 70s, just inundated by satellite data. Satellite data that gets used in pretty much all walks of life now to do different functions. But the satellite data able to sense the changes that are taking place on Earth, and we can see that, right? So hopefully this one will play too, but I'm holding my breath here. So what you're seeing is some areas of the globe, we're going back to 1880 to 84, some areas of globe here, right, on this 5-year mean, that are blue are colder than the 20th century mean. So the 1901 to 2000 mean, right? And where you see the orange and the red pockets, this is where it's warmer. And if it'll play for me, we'll see. You're going to see these changes throughout time, right? Let's kind of jump to the 30s here. 20s, here's the 30s, right? This was the Dust Bowl era, right? We know all about what happened here. So very warm across the U.S., right? If we can jump forward here a little bit to the 60s and 70s. These were 2 cool decades here across the U.S. There were other places that were still warm. But if we had advanced in time here, 90s, 2003 to 07, 2012 to 2016, right? So we can see an overall tone change, right? This is a lot of large parts of the world that are warmer than the 20th century mean. Our temperatures are warmer than they were in general, right? So that's the global picture. And maybe some of you are asking, how does, what causes this to come about? Why is the atmosphere warming? And it's a really simple explanation. We have the sun. Pretend we have nothing, right? No atmosphere here. We have the sun. We have the earth. We have visible light coming from the sun, which is shortwave radiation, higher frequency, visible light. It gets absorbed by the surfaces of the earth, the dark water, the dark land, right? And then it changes form. It's emitted as long-wave radiation, infrared light. Now we have these awesome things in the atmosphere called greenhouse gases, right? Water vapor, carbon dioxide. And what happens is the visible light still goes through these particles, gets absorbed at the surface, changed into long-wave radiation, and then emitted. And then all of a sudden these greenhouse gases absorb that energy. And when they absorb the energy, right, the temperature goes up. You add more of the greenhouse gases to the atmosphere, and the temperature has only one response, right, is to warm. And that's why we're seeing the warmth in the atmosphere as our gases increase. Now, if you think about water vapor, that humidity, the water vapor that's actually in the atmosphere, it contributes to about 40 degrees of Earth's current temperature. It's a way to think about it. Like if we didn't have the water vapor in the atmosphere would be cooler by about 40 degrees Fahrenheit, right? It's increased 5 to 10% in the last 50 years. Okay? The other big one we hear a lot about is the carbon dioxide. It contributes to about 20 degrees of Earth's current temperature. Again, without it in the atmosphere, it would be cooler, but it's increased 25 to 30% in the last 50 years. And this is a graph showing the increase in the carbon dioxide, where in 1958 we were below 320 parts per million, and now we're over 400. Okay, so we've added the greenhouse gases to the atmosphere, absorbs more of the infrared, the long-wave radiation from Earth's surface, and the atmosphere responds. But when we talk about temperature, it's only one variable, right? It's only one single variable of the whole suite of what we call weather, and we call climate, right? The changes in the temperature are doing a lot for a lot of places on Earth. I showed you the spatial map across the entire surface of the Earth. The glaciers and the ice sheets that are melting, right? That water flows off the land into the ocean and contributes to sea level rise. Anybody along the East Coast or have friends along the East Coast, when they deal with sunny day flooding events, right? Becoming a lot more frequent because of higher sea level, right? Now again, we increase our temperatures, we get a lot of different impacts, and I would argue here in Ohio, the big ones that are impacting us, along with the temperature, are the increases in water vapor. The amount of water vapor that's in the atmosphere. The warmer the atmosphere, the more water vapor is in it, right? And we're going to explain some interesting things that are happening. So let's take that global picture and let's start scaling it down, right? Let's get closer and closer to home here. So this is the observed temperature change. This is from the National Climate Assessment, and it's done 2 different ways. You can just take that dog walker way And across this region, 1.8 degrees Fahrenheit change from the early 20th century, 1901 to 1960, compared with 86 to 2016. A more conservative way is just to take those two periods and subtract them, right? And you get a change of 1.2 degrees Fahrenheit across the U.S. here. And I hope you guys are thinking 1.2 degrees Fahrenheit, right? We've gone up 10 degrees, probably 5 degrees today, 6 degrees, 7 degrees since we've sat in here, right? We're going to cool off very rapidly this evening, much greater than 1.2 or 1.5 degrees Fahrenheit, right? This is the difference between weather and climate. What has more heat, a boiling cup of water or Indian Lake full of lukewarm water? It's Indian Lake, right? Because heat deals with the total mass, the total kinetic energy. And so you can think about this warmer surface, this warmer energy system, right? More energy in it, more heat, okay? So a way to think about this. So when we look at changes downwind of Lake Erie here of more than 1.5 degree Fahrenheit change, now compared to the first 60 years of the 20th century, this is why it's a big deal, right? But there are a lot of details hidden in this annual average over this long period of time. And these are important details when it comes to agriculture, okay? We can start thinking about some of the impacts. And a lot of these impacts have been gathered through survey data. Maybe many of you have participated in this data out of the USDA Midwest Climate Hub or other facilities that are asking farmers, asking those concerned with soil and water health, what are your concerns? What are you seeing? What are the changes? So one of them is shifting growing zones, right? This is a map with the Arbor Day Foundation just showing the shift in the the hardiness zone. How cold are we getting in the wintertime? That's the key. And I'll show you a map here in a second that speaks to this as well. So we can look at these shifts, these red bands that you're seeing here. This is just looking at the shift in the hardiness zone. And it's been north and west, right? So what's an anecdote what's a story from this? Expanding Corn Belt north and west, right into the Dakotas, into Canada. Now obviously there are other factors, other variables, seed technology, those types of variables here. But this is a change between 2006 and 2012 of an additional 60,000 acres in these dark colored counties here, right? We've seen a shift in the Corn Belt toward the northwest. Now you can think, on a national level, this probably mitigates some nationwide crop loss, right? Because generally across the Midwest we have similar conditions, but oftentimes the east and west are very different, right? Think about the increased pressure from invasive plant species as those growing zones shift north and west, right? And those things, plant species and weeds. And all of this, it really depends on the management, and that's kind of another term moving forward. Like, I'm here to present the climate data basis, but I'm just an expert in the climate. You guys are the experts in the soil and the water and the farming and the crop production, right? And it's good that we can have a conversation and communicate back and forth what's happening in the climate, how are we going to manage it, how are we going to make the changes to adapt to it. And a lot of what you've already heard today fits very well into this kind of mindset here. So let's look at the temperature a little bit closer. Okay, this is the Corn Belt average temperature for December through February. Again, the dog walker, that purple line being the annual wintertime temperature across all of the Corn Belt. The blue line being the trend, and it's up about 0.2 Fahrenheit per decade, 2.2 since the late 1800s. So our wintertime is across the Corn Belt, is about 2 to 2.5 degrees warmer on average than it was in the early 20th century. Okay? If we look at the summertime, the trend is about half that. It's a little over a degree. So all of a sudden we can see we've had seasonal changes or seasonal differences in the temperature changes throughout this region here. And our winters are warmer and highly variable, right? And the summer's not warming quite as rapidly. And one of the newer things and newer studies that have come out just this year, really taking a closer look at this, I think are quite intriguing. Right, so this is the change in the coldest temperature of the year. Again, taking 86 to 2016 and subtracting off that first 60-year period. You see a lot of red and peach dots here. So across Ohio, the change in the coldest temperature of the year, we've warmed about 2 to 4 degrees. we're not reaching those extreme lows on average. We're about 2 to 4 degrees warmer than we were in the early 20th century, right? Now on the right-hand side, you're going to see this is the change in the warmest temperature of the year, our summertime maximum. You see a lot of blues right across Ohio, some 2 to 4 degrees cooler. Our summertime highs, those really extreme daytime highs, are cooling, right? Our maximum temperature during the summers actually decreased by 2 to 4 degrees across Ohio. So our warmer winters, our maximum summers during the daytime have gone down. And there's a couple of really cool explanations for this. First, decreases in the temperatures are really tied, the differences, because of the Dust Bowl era, right? I mean, the 1901 to 1960 frame has the Dust Bowl in it, right? Very dry time. When the atmosphere is dry, the air warms up much more rapidly than when you have moisture in it. Okay, and so that's a big difference there. But something I'm even more kind of intrigued by is some evidence showing that agricultural intensification has dampened those maximum summertime highs. Okay, because we've got more plants across the Midwest, we've got more irrigation, we've got more water vapor, more water evaporating into the atmosphere. When you've got more water in the atmosphere, you can't reach those extreme high temperatures during the summer. Oftentimes you develop clouds, those daytime highs stay cooler. This, I think, the impact of agricultural and regional climate, I think, is a phenomenal study, right? The phenomenal study of the impact that farmers and ag are having across the Midwest in terms of changing the local climate. So a little bit more about the temperature. So this is the observed number of very cold nights, 5-year means here going back to 1900 through 2014. The number of minimum temperatures fall below zero. Okay, so we can see our recent trends here in Ohio from the 70s to the current period. But hopefully you're kind of picking out this period here, the 20s through the 50s, where we had similar number of days below zero. Okay, so our local climate in here for Ohio in terms of the very cold nights is similar to this period in our record here. Okay, we've seen an observed increase in frost-free season length across the Midwest of about 9 days. Right, so this is kind of a regional picture, but 9 days. And coming with that are these frequent, what we call false springs. Right, we had what we thought was an unprecedented warm week last year in February, and then the same week this year we hit, actually Cincinnati broke this 78 for a 79 here. So, and it was across the entire state. So we saw a lot of advance of early spring signs here, at least up to about I-70. But these also cause some problems, right? And some management issues. So we can think about if we're rapidly advancing that phenological state, it makes some things susceptible to late season freezes. We're still seeing our late season freezes in April, right? March and April. Think about loss of nutrients in the plants themselves through dormancy breaks. Pests shifting northward. I talked about invasive species and weeds. But if you're increasing the pests, longer frost-free season length, you're getting more multiple generations, more generations. Pesticide resistance is increasing. Right? So a lot of these come along with this increased frost-free season length. All right, so that's the winter time. We know winters are getting warmer. Our nights aren't as cold. What about the summertime where the warming's a little bit slower, right, than the wintertime? This is the observed number of warm nights, days where our nights stay above 70 degrees Fahrenheit, right? So this is the strong trend here recently since the 60s of our number of days that stay above 70. Again, going back to this Dust Bowl era here in Ohio, where it was just so warm, right? It didn't cool off as quickly, even though we had some cool nights in here. We had some nights here that were much above 70 here locally as well. So our nights are warming, our maximum daytime highs have cooled. And this is what we see here, the number of observed very hot days, days above 95. We can see our recent trends really since the 60s. Much lower than the intense drought period that we had here in the 30s. All right, so there's subtle differences and changes that are happening that I think are really important to think about in terms of a crop or in terms of a field management and soil health and such, right? So here we are. What are the impacts from warmer nights? Well, obviously, if you're starting the day, if you're not dropping below 70, maybe you're starting 6 o'clock in the morning at 76, right? You got additional stress on humans and livestock, increased heat index, right? Heat indice. That's going to call for an increase in need for adequate cooling, right? Do you have enough cooling available for livestock? Do you have enough cooling, on an urban setting for sure inside the city? Is it cooling rapidly enough? This accelerated pace of growing degree days, right? If you're 76 at 6 and you're 86 at 9 o'clock in the morning, right? Things are shutting down, right? So you get this accelerated growing degrees. This could impact, regional crop rotations, field management options, all of these things that you guys are experts on. If you think about the cooling and the chilling hours or the pollination, grain, fiber, fruit production, obviously a lot of plants sensitive to these higher temperatures at night, lower productivity and reduced quality, okay? So that's the temperature side of things. And really, the next phase of the talk here is to talk about the precipitation, because this is the other big change that we're seeing here in Ohio, and it's tied to the water vapor. So again, we're looking at we're looking at the observed precipitation change in the annual precipitation here, observed precipitation change, across much of the Mississippi and Ohio Valley into the Northeast. It's some 10 to 15% increase in precipitation from now compared to the first 60 years of the 20th century. So our precipitation has gone up 15%. Again, this is hiding a lot of the details that I think are very important from a management standpoint. We can break this down seasonally. Across all of Ohio, fall precipitation is where we see our strongest trends, our upward trends in precip. If you go a little bit west of here, Iowa, Illinois, they're also seeing very strong spring precipitation trends, right? But and maybe just to the southwest of Ohio, across southern Indiana and Illinois, spring is another season with these strong trends. But here in Ohio, fall is our strongest trend. And this is just, again, the dog walker and the dog here. In fall, we're seeing between 1 to 1.5 inches of more rainfall now during our fall season than we did in the early part of the 20th century. Okay? Again, observed annual precipitation just for Ohio. Total annual precip in these 5-year means going back to the late 1800s to 2014. You can see our recent trends here. So, a couple of things. The heavier precipitation in Ohio falls across the south. The least amount across Toledo, right? 34 inches across Toledo, maybe 44 down across the south. So on average, Ohio is about 38 to 39 for the entire state. Our recent trends since the mid-1990s have us around 42 inches of rainfall per year, okay? But that's not falling, it's not distributed evenly across the year, as we'll see. And you can also see that the recent trends are much higher than what we have throughout our record. And this is based on about 26 long-term stations, right, that we have data going back to the late 1800s. But it's not falling gently. It's not evenly distributed throughout the year, right? We're seeing a lot of pictures like this. How many of you have seen more and more of these types of fields here? So this was the northern edge of Arcanum last summer. Sam clued me into this, about 5.5 inches of rainfall there, right? Very localized, but you can see what happens here. This was just a week later, I-75 east of Columbus shut down, right? Just the highway infrastructure inundated, not able to withstand the intensity of the rainfall that fell, right? This is called what? The flood-prone Blanchard River now, right? Not flood-susceptible, but flood-prone. This is a picture I took out in Darke County as well. This is just another graph, and this is going to be a little bit confusing, and actually I'm going to kind of elaborate on this a little bit. But this is looking at the heaviest 1%, or I should say the intensity of that 1% heaviest precipitation days. It's very hard to explain, right? I don't necessarily like using it, other than you can see a lot of red dots here showing across a large portion of northern Ohio. These very intense 1% events have increased 20% since mid-20th century. So I wanted to look at that a little bit closer. But obviously all of the extreme precipitation that we're seeing in Ohio has an impact on what's happening in Lake Erie. We know that, right? It's part of the picture. The farming is part of the picture. There may, probably very likely, right, a lot of other factors that are going into this, but these extreme weather events are part of the story. So we can look at the observed number of extreme precipitation events. These are number of events with precipitation greater than 2 inches on average for these 5-year periods. Here are the recent trends since the mid-90s, right? We've got 3 other peaks in our historical record. I'll throw the years up there. 1913, 37, and 59. Fall within these other 3 bands. These are the major flood years in Ohio, right? 13 being the largest, 37 the major Ohio River flood, and again in 59. So Eric Ricker challenged me to look at the precipitation a little bit closer because, again, I even have difficulty explaining this map, right? 1%, the heaviest 1% of events have increased 20%. So I wanted to break it down a little bit more. And so what I did was I looked at some long-term precipitation records from across northern Ohio. Essentially, stations that fall within the Lake Erie Basin or are very close. So don't get too nitpicky. There might be a station or 2 that are close, but just outside. But generally, we've got 21 stations where I was able to get adequate, most, I would say above 95% of the daily rainfall totals from these stations between 1950 and 2014. The idea being, let's compare the mid-20th century precipitation across this region to now and look at the trends a little bit closer. And what I wanted to do was break these daily rainfall frequencies out into bends, right? So we're going to start with the 3-inch events. These are essentially how many times on average across those 21 stations does a 3-inch event occur and 3 inch per day occur, right? And you can see these are breaking down into 5 years averages, 1950, 55 to 59, 60 to 64, and so on. There's not a large change, right? We generally get about one of these events on average every 5 years, right? For all of those stations. Now think about precip, right? It's not like temperature that's a little bit more evenly distributed. We get these really isolated events. So we're looking at stations and trying to capture the extremes, which can be difficult. But so I started here, right? I wanted to see what does it look like for the 3-inch events. Then I added on the 2.5 inch to 3-inch events, okay? So these are the total where we get more than 2.5 inches at these stations. Now it's about 3 times, right, during a 5-year period, whereas before we had about 2, right? So we can see that change. Add the next layer, anything above 2 inches. And you can really start to see the trend pulled out from this, right? We can see this upward trend here in the amount of the heavy precipitation events, 1.5 to 2 inch events, and then greater than 1 inch events, right? So we can see our trend here, if we were to put a trend line since the 60s of really high. We have to go back to the 59 period where it's anything like this, but I think this breaks it down a lot easier, and it's easier to see the increase in these extreme precipitation events. So on average, these stations see 40 to 45 events greater than 1 inch for each of these stations, okay? So then I wanted to pull and look at just a couple of the historical river forecasts. And I'm not a hydrologist, and I'm just pulling data and trying to look at, okay, the rivers and the runoff here in this area of Ohio. This is the Cuyahoga River here at Old Portage, and this goes back to 1924. These are historical crests here. So 24 being a large one. Just for reference, the 59. And then you can see these cluster of events that have occurred that are quite high here in the 2000s. This is the Huron River in Milan. So 69 being the largest historical crest in this one here, right, in the recent period. And then some of the ones in the northwest were quite interesting. This is Tiffin at Stryker, right? So this is the 1913 event. Some clustered in the 40s and 50s, and then this large clustering since the late 1990s here of historical river crests, right, in this part of in this region here. Okay, so just kind of an interesting thing. But you know, we have these extreme precipitation events. Kevin pegged it. They're isolated, right? they're not necessarily well forecast, right? Model forecasts don't give us extremes most of the time. They give us means or averages over a large ensemble. They're very hard to predict, right? What are the impacts from these precipitation extremes? You guys, we've talked about it a lot today, right? Not exactly, or not, what am I trying to say? We've talked a lot about the nutrients, right? We've talked a lot about incorporating manure and such, which are very much a part of this story, right? When we think about soil movement and loss, how do we mitigate that? Perhaps with the reduction in the tillage, right? Or cover crops. These are measures that we can think about taking to help not only profitability and sustainability, but also help these environmental impacts. Potential flooded manure lagoons from these extreme precipitation events. I think it, as Sam told me, it depends really on the systems and how extreme the precipitation events are. But how likely are these? Are we prepared for these types of events in the future? What about the loss of field work days, right? The delays in planting. How many are worried about the wet fields right now, right? The delays in planting, the delay in harvests. So where are we going, right? When we think about this, when we think about where we're going, we have to ask the question, what are our best tools to assess where we're going? And we rely on the models, okay? Models are imperfect tools, right? They're imperfect. They're not going to give you a perfect answer. But we run a lot of models, and we vary the conditions that we run the models so that we can get a range of options, a range of likelihood, and so we can become more confident in what we expect, right? So this is one of the models looking at predictions out to about the mid 21st century here, 2040 to 2070. And temperatures on average in Ohio of about 4.5 degrees warmer on average. On average. We've gone up 1 to 1.5. We're talking about 4 by 2070. A lot of that driven by the wintertime changes. So here's a graph showing number of nights where we fall below 32, decreasing by about 30 days. Right? So we've seen a 9-day increase in frost-free. Now we're looking at perhaps up to 30 by 2070. What type of impacts does that have? This was a cold hardiness zone, also looking at models that changes between, say, 71 to 2000 and, again, mid-21st century. If you look at the scales here in the cold hardiness zone, essentially much of southern Ohio is what's currently in southern Tennessee and northern Georgia, northern Alabama, in terms of cold hardiness, right? Again, shifting the plants, shifting the growing, the crop production. What are we going to see? What about the precipitation? Again, out to mid-21st century, we're looking at 3 to 4 inches more of rain per year compared to what we've seen in the past. It's not going to be evenly distributed. We've seen these seasonal trends, these seasonal changes. But also we project an increase in the number of consecutive dry days. So you can have more drought, short periods of drought, broken by intense precipitation events. We're changing the hydrologic cycle. Because as we warm, we intensify the evaporative cycle, right? We're evaporating that moisture a lot quicker as well, right? And then in terms of seasonal changes, there is a projection of an increase in the spring precip here of about 10 to 15% as well. So we'll essentially see large changes in our spring, summer, and our winter, spring, summer, and our fall precipitation into the future. So again, I mentioned earlier, it's really, my goal is really about starting a conversation or continuing a conversation, right? This was a Farm and Dairy article that came out on a paper that came out last fall. Looking at the pros and cons, where we're heading, what are the pros and cons? What are the things that we need to think about in terms of farm management, right? Foraging. Forage, right? Depending on the crop, some of it may increase, some of it may decrease. It's really as a community or as individuals to think about your own situation. How will you be impacted by warmer temperatures? How will you be impacted by extreme precipitation on a personal level? Thinking about reducing maintenance costs for beef cattle, right? Because you can increase your grazing days, frost-free length. What do you do about heat stress? Additional heat stress, additional cooling, right? There's a lot of these, and I already talked about the pathogens and the loss of nutrients and things that, as we move forward here, there's a lot that we could talk about in terms of how do we adapt, how do we prepare to the changes that we see coming. Our soil and water, very important, right? We can think about the seasonal precipitation changes and how our water availability is impacted, right, for crop production. Healthy soils impacted, right? Erosion, compaction, and loss of organic matter. A couple weeks ago, I got to meet Frank Gibbs, right? Night crawlers, a lot of organic material. That's what we need. But how does changing soil temperature and water availability impact that organic matter? How does the erosion impact just the soil health, these intense extreme precipitation events? You can think about associated off-site non-point pollution sources, right? Increasing tillage intensity, crop selection, harvest dates, changing planting dates. That'll all impact the soil and the water. Surface and groundwater as well, evapotranspiration changes and recharge. So the list goes on in terms of the obstacles or the challenges. It's really up to all of us to think about how we adapt. And I think, to put it in perspective and something to think about, we talk about these migrating climates. So in Ohio, by the end of the 21st century, our winters are more like the Carolinas, Virginia, current day, and our summers are more like Arkansas. Be a farmer in Arkansas, right? And if you think about your sustainability and profitability into the future or the next generation, what are the challenges that lie ahead for this? And just being prepared for it, not being scared of it, and having those conversations about it. So that's really what we talk about with the adaptation. We have to increase the knowledge of our local threats. We have global threats for sure, but we have these local threats from intense precipitation events and our temperature changes. So the best thing we can do is plan our actions, assess the vulnerabilities, investigate the options. How do we maintain the sustainability of healthy water, soils, and crops? So there's a lot of resources. How many know we have a state climate office? A few of you. We have a state climate office, and you can reach us. We have a website here with a lot of good materials. I think the USDA Midwest Climate Hub, there's a lot of good information out of there as well, including Climate Change and Agricultural Report that came out in 2012. A lot of great work that went into that. Vulnerability of specialty crops. I didn't even really touch on a lot of the specialty crops impacts as well. This is our website, and you can get some hydro blog, a video blog here of the hydro and climate assessment. That'll be starting back up on a weekly basis. Some 7, 30, and 90-day climate maps. And I want to stop there. I've got a couple more slides to show you of a product that we've been working on, but I think we've got plenty of time, don't we? Yep. Let's stop there, and I'll take any questions that you have, and then I'll show you this new product. Yeah?
I had a question. You showed a couple of the graphs that had the increase, I think, in stream flow, river flow, and a lot of that has increased in the last 20, 30 years. How much of that has it been kind of normalized? How much is that related to like impervious surface? Yeah,
so thank you for reminding me. I mean, the one thing I wanted to say was this was just a quick look, a quick dirty look, right? Not being not normalizing for land surface changes, land surface conditions. That's all part of this. We have to think about that, in a larger context. It really was just a look at looking at the clusters of precip and tying it to the extreme. But you're absolutely right. I mean, water development, even the picture I used here from the NRCS, right? This was development in the watershed that led to this, right? So that's part of the issue here. So again, this is a complex issue, complex problem with a lot of tentacles that go into many other areas. That's why climate scientists alone can't solve the issues. It really takes a community of engaged partners to think about the challenges. Yeah?
So the West is getting drier and we are getting wetter is kind of what the trends are showing. Has there been any discussion about seeing migration of people into our region and how that's going to affect our food supply with land availability?
I'm not so familiar with the West. I'm more familiar with the cities that are really challenged by sea level rise and lowland flooding. So there have been a lot of studies. New York City, Houston, Tampa, and Miami for sure. When you talk about migration of people, there are neighborhoods that are being challenged now by the sea level rise. And of course, as the levels get higher, then the high tides inundate more and more. Any storms that come ashore obviously have more storm surge. So there is that thought, right? I mean, there are some cities like Columbus that are increasing in population, for instance. There's this idea that it's, again, a complex issue where it's more than just about weather and climate, but it's all the socioeconomic impacts as well from migration of people as well. We live in a very water-rich area where the western United States is very water-starved. We have the Great Lakes. I'm sure they would like some of that water, right? There's a lot of talks on that, So I think certainly that's part of it, part of the conversation moving into the future. Are there any other questions? Okay. So real brief, and again, apologize for kind of flying through this a little bit, but I did want to, we've been working on, through an investment with Extension and a couple of our offices at OSU on a Connect and Collaborate grant to kind of help with this historical precipitation forecast database, right? This idea that you can look at a forecast now and also kind of get a previous forecast here. So this is what we call our farm app. This is farm.bbcrc.osu.edu. This is the splash page here. You can click and view as a guest. It'll allow you to draw your farm, right? And then from here, it'll give you the 50% chance, the threshold in 12 and 24 hours, okay? With some caveats in terms of this is not meant as a compliance tool, right? This is meant as a tool to use. These are National Weather Service forecasts. We get these forecasts as well. And then also a statewide condition map that's kind of a dirty look, a quick look. You can just click on this, and then it'll give you the 12 and also the 24-hour based on the SB1 thresholds, whether the precipitation is within those 50% thresholds here for both fertilizer and manure. And again, you can go back and pull out a previous date. So I did that this morning. This is the February 24th here. The 50% chance of 0.78 inches of rain for this particular area in 12 hours and also 24 hours. So this is another tool that right now we're kind of pulling to a close, but we would like some additional feedback from public that use it. We'll have a feedback form here that you can use as well. So I just wanted to introduce you to that, to use it, to utilize it, again, and not as a compliance tool, and there's caveats on there. This is not meant to fulfill anything other than if you need a previous forecast, we have the database as well. All right?
All right.
Thanks.
Thanks, Aaron. Let's welcome him.